All right, well, welcome everyone. Happy Friday. Hope you had a nice week. For those of you joining us for the first time, my name is Brian Jackson. I'm a professor in the physics department at Boise State University, and you are joining the live stream of the first Friday astronomy event that the Boise State Physics Department hosts every month. These events, as I say, take place on the first Friday of every month, all through the summer, all through the fall, all through the winter. And so if it's the first Friday of some month and you're looking for something to do that evening, this is a good option. These take place in the fall and the spring, 7:30 p.m. Mountain Time on that first Friday. And then over the summer, they take place at 8:30 p.m. Usually when these events take place in person, after the lecture, we take everyone up to the observatory and we do some stargazing. Of course, everything is virtual right now, and so we can't do that. But hopefully, when things get back to normal, you would all be welcome to join us again after the lecture to do some stargazing. And it has been really fantastic weather for the last several weeks to do stargazing. So I want to invite you all, if you are attending this on the live stream over YouTube, you are welcome to ask questions. On the live stream chat, I am monitoring that as well as the video stream. And so I'm going to show you how to do that in case that's confusing. So I think right now you can see the live stream. You can see our speaker who's queued up to speak for us tonight. Over here is the live chat window. And here's where I'd like you to answer your questions. So of course, our speaker would be very happy to take your questions after the lecture. And if you have questions, please put them in the chat window over here, because I will relay them to our speaker at the end of her presentation. As I said, these take place on the first Friday of every month. And so the next one of these events will take place on October 2nd. That's the first Friday of October at 7:30 p.m. We will have a guest speaker, Dr. Laura Mayorga from the Space Telescope Science Institute. And she's going to talk about extrasolar planetary systems. It should be a really fascinating talk. And we have a really nice talk queued up for tonight. Our guest speaker is Professor Darci Snowden of the Central Washington University. She got her bachelor's degree in physics from Harvey Mudd College in California and a PhD in geophysics from the University of Washington. She spent a lot of time working with the Cassini mission, and I think she's going to talk a little bit tonight about some of the really neat things that Cassini found in the Saturn system. Her expertise is in atmospheric chemistry and physics, also some magnetohydrodynamics. You're going to hear some interesting things there. Maybe she'll give us a little hint of her public outreach in which she does high altitude ballooning. Those of you who were with us last month, you might remember Dr. Paul Berhaj's talk on the same topic, really fascinating experiments. And with that, I'm going to turn it over to Professor Darci Snowden. Do you want to take it away?
Sure, thank you. I'm not going to give you guys too much on high altitude ballooning, but I will talk a little bit about ballooning in general at the end. So let's see. Oh, I think I have to get permission to share my screen from you. Let's see. There we go.
Okay, you should have it now. Go ahead.
Yeah, I got it. Okay, let's see. Make sure that's the right one. Okay. Okay, so welcome everybody. My name is Darci Snowden. Like Brian said, I have worked on Titan science basically my whole scientific career. And what I wanted to talk to you guys about tonight is just some general fun stuff about my favorite body in the solar system, Titan. And so the title of my talk is Peering Through the Haze, Titan's Fascinating Atmosphere and Surface. So it's going to be a little bit less about my personal research, although I'll hint about that at the end, and a little bit more about just the most interesting things we've discovered. But just to start off and give you a little bit of background about what I do, I'm a planetary scientist, of course. I'm a professor in the physics department, but science-wise, I consider myself to be a planetary scientist. The type of planetary science I do is called space physics. And that's basically studying electrodynamics in space. So electric and magnetic fields in space and charged particles in space. And in my case, how they interact with atmospheres of planets and moons. And then I also study aeronomy. So that's the physics of the very upper atmosphere. And I mostly write computer models, but I also do some spacecraft data analysis. And my personal specialty is understanding the interaction between Titan's atmosphere and Saturn's magnetosphere, or the region that's dominated by Saturn's magnetic field in space, and as observed by Cassini, which means I've used my models to help interpret Cassini data. But for this talk, like I said, my goal is just to kind of do a little bit of advertising of Titan as an interesting body. So I'm a professor. I talk to a lot of students, and a lot of students maybe have heard of Titan, but couldn't tell me, what Titan is, what planet it's the moon of. So I want to, get the word out that Titan is pretty much, in my opinion, the most interesting body in the solar system. So that's my goal for this talk. And I'm just going to start out with some background, just some history of Titan exploration, and then I'll talk a little bit about the Cassini mission. And then we'll look to the future, and I'll talk a little bit about some future proposed missions to Titan. So right here, this is Titan. This is what it looks like if you were to look at it with your naked eye in the visible part of the spectrum. It's a big orange blob, and we'll talk about why that is in a little bit. So if we go all the way back for the background of Titan, it was discovered by people, this guy in particular, Christian Huygens. In 1655, Christian Huygens was a big physicist and astronomer at his time, lived at the same time as Isaac Newton. One of the things that he did was tinker around with telescopes at that time. And of course, Saturn was, just like today, a really beautiful and interesting thing to look at through a telescope. So he was looking at Saturn. He actually discovered the rings of Saturn, but he also discovered this large moon orbiting around Saturn. And this is just a sketch of some of his data. Other fun fact, he invented the pendulum clock. So a lot of these early physicists did a lot of different things, and he is no exception. But that was the discovery of Titan, 1655. Going forward, right, quite a few years, 300 years almost, we're learning something new about Titan. So Gerard Kuiper, whose name might sound familiar because we named a belt of objects around him called the Kuiper belt, he discovered that Titan has an atmosphere, which is what you were looking at when you saw that picture of Titan. That orange color is from the atmosphere. And the way that he discovered this was by looking at the spectrum of sunlight reflected off of Titan. And then this right here is a plate. This is how astronomers used to get data, is by exposing the light to a plate. And what you're seeing here is both the spectrum of Saturn, that's what's labeled with S, and Titan, T. And where you're seeing these dark bands, that's what physicists call absorption features. That's where light from the sun is being absorbed by the atmosphere. And these absorption features are characteristic of methane. So he essentially discovered that Titan's atmosphere has methane in it. And that meant that Titan had a dense atmosphere at all in the first place, which is unique for a satellite. And he recognized that this should be quite an anomaly, because he knew that Titan was a moon, a relatively small body in our solar system. Small bodies don't have a lot of gravity, right? Like the moon doesn't have a lot of gravity, and it's hard for those bodies to hold on to gases at all, let alone light gases, like things that have hydrogen in them. So he was surprised to find methane on Titan. Okay, going forward a little bit more, now we're starting to send spacecraft in to space and get some closer images of the bodies in our solar system. And I like talking about these images because even though 1979 seems like a long time ago, really it's not that long ago when we're thinking about how long ago that Titan was discovered in general. Like my parents were still kicking it around in 1979. And in 1979, we sent Pioneer 11, which looks like this. This is a replica of it, into the outer solar system. And it flew by Saturn and took this image. And it flew by Titan and it took this image. And basically, Pioneer did some very basic science. But in terms of what it did at Titan, it confirmed that Titan had this atmosphere. This is our first really nice image, showing really that Titan is this boring orange blob, but what we're looking at is a dense, interesting atmosphere. Going forward a few years, I like to show this or some image of the trajectory of some of these early outer planet probes. This particular graphic shows the trajectory of both Pioneer 11 or Pioneer 10 and Pioneer 11, which is the one I just talked about. But it also shows the dual Voyager spacecraft. And the Voyager spacecraft took advantage of this somewhat rare planetary alignment where they could do this amazing planetary tour throughout the outer solar system. But I like to point out the differences here. Once they both got to Saturn, you can see that Voyager 2 and Voyager 1 diverged in their trajectories. Voyager 2 went ahead and flew by Neptune, Uranus and Neptune, and took the first images of those planets. Voyager 1 actually went off in another direction and did not have a close encounter with those two bodies. And one of the reasons why scientists decided to do that is because they wanted to send Voyager past Titan. They thought Titan, even back in these days, was so interesting that it was worth it to them to send Voyager close to Titan and miss being able to see or having a close flyby of these outer planets. So Voyager 1 and Voyager 2 both visited the Saturn system. Voyager 1 is the one that actually had a close encounter with Titan, a close flyby. And these are some images from these spacecraft. You can see Saturn, this image already looks a lot more clear than what we saw from the Pioneer spacecraft. And you can see the nice gaps in the rings and things like that. With Titan, you can see, again, that orange atmosphere. You can now start to see these hazes of gases, of other type of particulates forming in Titan's atmosphere, which are very characteristic of Titan. Again, we can't see down to the surface. We're just seeing the atmosphere, but it made some other measurements. We got a confirmation of the mass of Titan. We actually more precisely measured the radius of Titan, or figured out what the radius was. And Voyager discovered that it was only the second largest moon in the satellite or the solar system rather than the largest moon. And Voyager did things like measure the main constituent of Titan's atmosphere, which is nitrogen. We didn't know that before Voyager flew by Titan. And this, by the way, this is an image of another replica of the Voyager spacecraft, which is at JPL. And it's pretty big. It's a pretty cool looking spacecraft, pretty large. All right, so I like to show this graphic just to give you guys an idea. So, you know, in our minds, somehow we split the objects in the solar system into planets and moons. But if you're a planetary scientist, that distinction isn't so important. Titan is a large body in our solar system. Like I said, it's the second largest moon, but it's actually larger than the planet Mercury. Okay, so it's larger than the planet Mercury, and it's smaller than Mars, but it's not significantly smaller than Mars. So it's a fairly large body in the solar system. And what really makes it unique, again, is the fact that it's the only moon, the only body orbiting a planet that has a really dense atmosphere. So here, looking again, this is a nicer image of Titan yet. This one is from Cassini. Just giving some basic facts about Titan. Like I said, it's a fairly large moon. Its radius, which is half of its diameter, is about 1,600 miles. Its composition of the solid part of Titan is about 50% water ice and 50% silicate rock. This makes it what we call an icy moon. And all of the moons that formed beyond Mars are what we call icy moons. The atmospheric composition, it's mostly molecular nitrogen, which makes it interesting because that's just like the Earth's atmosphere. And then the next largest constituent is methane. And then there's a lot of other interesting molecules as well that are present at lower levels than methane. And then the atmosphere, like I said, it's substantial. It's very dense. And in fact, the surface pressure at Titan, so the pressure of the atmosphere at the surface, is 1.5 times that of the Earth. So the Earth's surface pressure is 1 bar, at Titan, 1.5 times. So that's interesting as well. And kind of mysterious. Why does this small body have such a dense atmosphere? It's unique. Saturn and Titan are about 10 times further away from the sun than the Earth is. That means they get a lot less heat from the sun and they are cold. Okay, so the surface temperature is about -300 degrees Fahrenheit. It orbits about once every 16 days around Saturn, and that's also the length of day at Titan because it is what we call tidally locked, which means the same side of Titan faces Saturn just like the same side of the moon always faces the Earth. And then lastly, it has no internal magnetic field, which seems like kind of a detail, but it's important for me. That means its atmosphere is kind of exposed to space, which actually makes it even more mysterious that it has this atmosphere, because space can be stripping it away like we think happened, for example, on Mars. All right, so that's the background. That's kind of the history of Titan exploration. Now I want to go forward and talk about the Cassini mission and what we learned about it. So everything I've showed you so far, we've just seen this orange blob looking at the atmosphere. I'm going to show you that Cassini has showed us that Titan is even more interesting than we thought it was looking at those images. So the Cassini mission, I like to show the timeline because it shows how long it takes to develop these missions, how long it takes for the spacecraft to actually get to where they're going, and then how long they can run and collect data. The Cassini mission began in 1982, which is actually the year I was born, okay? But it took 15 years to develop the mission and build the spacecraft, and it didn't launch until 1997, okay? So I was chilling in high school when this thing launched. I can't say that I remember the launch. I probably wasn't paying attention at the time. Okay, but it took another about 7 years to get out to Saturn, and this is its trajectory as it cruised out. So again, we have this nice thing where we actually got to fly by Jupiter. We used Jupiter here for a gravity assist to get out to Saturn, but Cassini also did some interesting science at Jupiter as well. It took a lot of interesting data for over 12 years, and then the mission actually ended in September 15th, 2017. And maybe some of you guys were paying attention when that happened. It was covered pretty well by the media, but they had to end the mission because the spacecraft was starting to lose its navigational capabilities, running out of fuel. And they wanted to have a nice planned ending. They don't want to leave a uncontrolled spacecraft orbiting around Saturn. And they also, a lot of the instruments were still working really well. So they knew that if they sent the spacecraft near Saturn and into Saturn's atmosphere, they'd be able to collect some really excellent data. So that's what they did. They sent the spacecraft into Saturn's atmosphere, and there's a really cool movie I didn't include, but the spacecraft tried to point its antenna towards the Earth as long as it could to send data back until it just lost pointing, and then at some point later it disintegrated in the atmosphere. Cassini is what's called a flagship mission. So that's the most expensive type of mission that NASA pays for, the biggest type of mission. So this is a big spacecraft. This spacecraft was about the size of a school bus, and that's what you're looking at here. There's got some shielding here, but all of these things around the spacecraft are instruments. Okay, this is its high gain antenna. That's the thing that we use to send data back to Earth, but it's also an instrument that we use to do science. I'll show you guys a little bit about that. And then I want you guys to note this little guy here. That's called the Huygens probe, named after Christian Huygens. Also imaged a picture of it here. And this is the probe that Cassini released and descended into Titan's atmosphere and actually landed on the surface of Titan. So just looking, this is a graphic of the spacecraft showing some of the instruments. The Cassini spacecraft had 12 different instruments. This one's graphic is showing 10 of them. And it's a mix of cameras and what we call plasma and fields instruments. These are instruments that are that measure in situ, which means in place. So they actually take a sample of the environment that the spacecraft is actually flying through. The gases are measuring the fields, right? And then other ones are just taking pictures. There's times when Cassini was collecting data, and then there were really boring times during its orbit where it just had this antenna pointed back towards the Earth, and it was downlinking that data back for us to look at. Just to kind of keep with what we were looking at before, I like to throw this image in. This is Cassini's first image of Saturn. So again, you can see like kind of an improvement in our imaging capabilities. And this is still pretty old technology to us now. We all probably have maybe better or similar cameras on our phones because remember, this spacecraft was launched in 1997, which is quite a while ago. But we're getting a really nice picture of Saturn here. And this was taken from about 17 million miles away as Cassini approached the system. The This is an older picture, but I like to show it before I talk about what happens with Huygens. This is like my before Cassini picture. So I told you that mostly what we knew about Titan, right, is that it was big. It had this really dense atmosphere. But if you looked at it, you took a picture invisible, you just got orange. You just saw the atmosphere. But of course, we have some tricks up our sleeve. And we have Hubble and also some ground-based telescopes that could peer through that atmosphere at different, what we call windows, different bands of the electromagnetic spectrum that actually penetrate through the atmosphere to try to get some idea about what the surface is like. And so this is kind of an idea, an image that gives us an idea about what we knew about the surface before Cassini. And basically we knew that there was some dark regions and there were some light regions. And Huygens was designed to land kind of near a boundary, but in a dark region. Another thing that we knew about Titan that is super interesting, but kind of the thing, again, one of these things that makes Titan one of the most interesting bodies, maybe other than the Earth in the solar system, is the fact that at the temperature and pressure in Titan's atmosphere, methane, which is CH4, is near its triple point. Okay, so on Earth is such an interesting planet, and we're able to live on it because the pressure and temperature in the Earth's atmosphere is close to the triple point of water. And that means that water on the Earth, on the surface of the Earth and in the atmosphere, can be in liquid, gas, and solid form. And of course, we experience that, right? Ice, water, and then, you know, if on a high humidity day, there's water vapor in the atmosphere. Okay, at Titan, we know that this is true even before we sent Cassini. We knew that this was true for methane. So this old graphic is a pre-Cassini graphic where scientists imagined maybe on the surface of Titan, you could have seas of liquid methane, you could have liquid methane rain, you could have clouds, all of this interesting stuff happening. So if we go back to this image, some scientists thought maybe these dark regions were liquid methane seas on the surface. So going forward to the Huygens probe, this is a graphic. This is not a real picture of what its descent may have looked like. This is in white. It landed on 14th of January, 2005. It was actually released in December of 2004. And so this is kind of what scientists thought maybe the landing zone would look like. The Huygens probe was designed to land either on solid surface or on liquid, since they didn't know. Might as well throw a movie in here. This is a movie that's going to show some animations, but also some real imagery from that Huygens probe as it descended through Titan's atmosphere. And by the way, it took 2.5 hours to descend. Again, Titan is small. It doesn't have very much gravity, and it's got this really dense atmosphere, which means parachutes really have no problem slowing down a spacecraft, which is not true at Mars, as we see every time we land something on that. So I might do, well, let's see if I can get away with this. No, I'll leave it. So basically, Cassini released the probe as soon as it got to the Saturn system. It didn't fly around a bunch with it. It went ahead and did this right away. And Titan has an atmosphere, so this probe has a heat shield to protect the instrument. And then it deployed a series of parachutes to slow itself down. And now we're looking at some real imagery. So we're actually peering through the haze, like the title says, for the first time. And you can see, I'll just pause it for a second. The first things you can see that indeed the surface looks interesting. You've got bright regions. So they're reflecting sunlight differently than these dark regions, which is indicating a compositional difference or maybe a difference in the roughness of the terrain. And then I'm going to pause it again here because I want to point out what it's talking about. So this is one of the coolest things right off the bat we got from the Cassini mission. And that's the images that we got from the Huygens probe of drainage channels on Titan. If you don't know where to look, you wouldn't see them maybe in this image, but they're here and also here. Okay, and I'll show more images of drainage channels, but these are very similar to drainage channels you would see if you took an aerial photograph of a region on the Earth that had water flow at some point and the riverbeds had dried up. So right off the bat, this is not mysterious like Mars. Was there liquid? Isn't there liquid? Right off the bat, we got indications that there has been liquid flow on the surface of Titan. So it's going to land in the dark region, which again, like the video says, scientists thought maybe that could be liquid seas, but it's not. Okay, and again, this is still real images. Okay, so this is what the surface of Titan looks like. Okay, real images taken by the Huygens probe. There you can see the parachute going across. And then this is just another animation. Okay, but this is really cool. I think everyone should know that we've landed a probe on Titan, one of the moons of Saturn. And saw some really interesting things. But let's go back to, if I can get this to go forward, the view from the ground. So this again is a graphic. That's not a real picture. This is a real picture. So when Huygens landed on the ground, it survived for about 90 minutes. And really it only was able to take this one picture and send it back up. And it was only designed to do that because it takes a long time to, especially in those days, transmit the data for a picture. So it sent the data up to Cassini, and then Cassini sent the data back to Earth. But what it saw on the surface of Titan is rounded ice rocks. So on the icy moons, ice is just like rocks on Earth. It's so hard. It's not like ice is on the surface of the Earth where it can melt. It's rock hard. And the fact that the ice that it saw was rounded indicates that it had been eroded by some kind of fluvial flow. On the Earth, we only see rounded rocks like this in things like riverbeds, where we know the rocks had been bounced around and that smooths them out. It didn't land in liquid, but when it landed, the heat on the spacecraft actually caused methane to evaporate from the surface. And the spacecraft was able to measure that, as well as some other gases, indicating the surface was at least moist. It wasn't totally dry. And it had the consistency of wet sand. Okay, so really it didn't land in lakes, but still really interesting stuff. But that was our that's our view from Huygens of the ground. So the rest of the mission, we still had this problem that we had to look through this atmosphere in order to see Titan's surface. Like I said, those scientists have tricks up their sleeves. This particular graphic here is actually for the Earth, but it works pretty well for Titan as well. And what it's showing is something called atmospheric opacity, or how see-through the atmosphere is at different wavelengths of light. So for the Earth, it's got quite a bit of opacity. It's pretty see-through for visible light, not totally, but that's why if I take a picture of the Earth from space, I can see the ground. I'm not seeing the atmosphere because the atmosphere is not absorbing a lot of that visible light. But in other regions, the atmosphere of the Earth is totally opaque to different types of light. But one region, it's pretty transparent, and that's the region of radio. Okay, so these are longer wavelengths of light on the order of centimeters. You can totally peer through down to the surface of the Earth, and that's also true of Titan. So the main way we image the surface, at least globally, is by looking with actually the same antenna that we use to communicate from the spacecraft to Earth, looking at this high gain antenna and using it to bounce radio waves off the surface and then measuring what's reflected back and making images out of that. So not from visible light, but from radio, wavelengths of around 2 centimeters. And you can see the surface. I'll show you guys some images because the reflectivity depends on the orientation of the surface, how rough it is, and what the surface is made of. And just because movies are fun and NASA has really since the time that I've done planetary science, it's really like upped its game in terms of the stuff that it provides people to teach the public how planetary science works. This is a program called Eyes on the Solar System. And again, it's just a movie and animation of how Cassini and other spacecraft have toured through the solar system. And this is showing how the high gain antenna points at Titan's surface. And what it really does is it gets these swaths or these bands of data. Okay, so when you look at an image of Titan, maybe a global image of surface of what it's data from the surface, you often see these little bands. Those are the bands where the radar happened to have scanned through. The rest of this is filled in by other imagery means in the infrared. That's the different colors. And this particular globe that we're looking at, that was just one flyby of it taking some data. This globe is basically all of the data that it has. So it didn't collect all of this data in that one flyby. But if we look at what we discovered from that radar, again, right off the bat, we're getting all of the cool stuff from Titan. This is an image, by the way, of all of the radar data that it's taken from the northern pole. So this is the very northern pole of Titan. And again, you can see those radar swaths here. You can see some gaps in data. The rest of this is different types of data filling in the gaps here. But what we saw with the radar was really dark regions, okay? Really dark regions, really smooth regions. And those are liquid seas or lakes of methane and ethane, or methane or ethane, on the surface of Titan. Okay, so in fact, even though we didn't see big seas where Huygens landed, there are big seas of liquid methane on the surface of Titan. All the seas are named after mythical sea creatures. Okay, the largest one is called Kraken Mar, and it's larger than Lake Superior. So this sea here is about the same size as Lake Superior. This one's obviously larger. And Lake Superior, by the way, is the largest freshwater lake on the surface of the Earth. So that gives you an idea about how big they are. And you can see they're pretty interesting. They're interconnected, a lot of them. And then there's a lot of little lakes too. And the joke was kind of that Titan is the Minnesota of the solar system. Okay, but these lakes, even though they're colored blue in this image, again, that's all false coloring. They're filled not with water, with liquid methane. And here's just another image. This is actually a near infrared image, which is just another way you can image the surface. Here, you can see some of those same lakes. And actually, on this one, you can see some clouds in the atmosphere. This was one of the last images taken by Cassini of Titan. So this is as the northern pole entered summer. So we were anticipating these clouds as the seasons changed, and then lots of little lakes. So this, I don't know. If you don't think that's cool, I don't know what is. Super cool. I told you I'd show you another picture of the channels on Titan. So that's what I'm showing here. This is a different image, but it's similar to what the Huygens probe observed of channels carved in the ice. So again, the surface of Titan, it's not a lot of silicate rock, it's mostly ice. Okay, but the liquid, just like water can carve out channels on rocks on the Earth, liquid methane can carve apparently channels in the ice on Titan. And if you're hiking, you might notice when you're high up in the mountains that the streams are pretty small, okay? And then those streams combine as you get lower and lower, say towards a valley, to create larger streams, and then eventually rivers, and then maybe there's a lake at the bottom. So that's what we're seeing here. And what this is called is something called dendritic river channels, and it's very characteristic of liquids flowing from higher altitudes to lower altitudes. So we know that there is liquid flowing on the surface of Titan. These images, they're actually dry. So that means that it doesn't happen all the time. And in fact, Titan, again, it's much further away from the sun than the Earth, which means it's colder. And also it has really long seasons. It takes 29 years to orbit the sun. So models seem to suggest that if this liquid is coming from the sky, coming from clouds, The rain showers might be quite infrequent, maybe a few times a year, or maybe even once every 1,000 years, depending on the model. But the storms could be also very strong. So you'll get a lot of liquid methane coming down in a short period of time, which could be sufficient to carve these channels. So we've kind of confirmed what scientists thought might be true, is that Titan has this really interesting methane cycle, just like we have a hydrological cycle on the Earth, where we've got reservoirs of liquid, we've got clouds, and we have precipitation of liquid from those clouds. So we have this exchange between the surface reservoirs and the atmosphere. And we could also have, just like we do on Earth, interesting interactions between the subsurface as well, subsurface water coming up and things like that. Okay, so very cool. I'll come back to this image again in a second. Just another fun image. So I said there's rain here. I said there's evidence of rain happening here. Cassini actually did observe rain on Titan. And this image is our evidence of rain. What you're seeing, these are duplicate images. This one just has more labels on it down here. You're seeing clouds here, and this is a near infrared image. Again, this is not a radar image. These near infrared images can actually see stuff in the atmosphere. So we're seeing low clouds, just like rain clouds on the Earth in the troposphere. And here we're seeing the surface. I just want to point this out. Clouds kind of pass over this region, and later we see the surface darkening like it's wet, okay, from some liquid. These clouds were observed in the southern pole. So not the North Pole where all those lakes were, in the southern pole. And the southern pole does also have lakes on Titan. It has this big one, Ontario Locust, but not as many by far, okay? So this is the only big one on the southern pole. So there's this dichotomy that's also kind of interesting. There's also higher altitude clouds, just like there are on the Earth. So these clouds form because moist air is rising up, and the moisture, the methane in that air is condensing. But we also have stratospheric clouds, which is in the higher level, a little bit higher in the atmosphere. And these clouds form when stuff that from interesting chemical processes that is formed higher in the atmosphere actually comes down and downwells. And so we get these big polar hoods or big clouds and hazes forming on Titan higher in the atmosphere. So this is a cloud, but also those hazes you could see in those Voyager pictures are from this downwelling of gas from higher in the atmosphere. If you look at the surface, another thing you might want to look at if you're a planetary scientist is craters. Craters are how we age surfaces in the solar system, how we tell how active the surfaces are geologically. At Titan, there's not a lot of craters for as big as it is. There's only 8 named craters, which means they're big enough to bother giving a name to. And there's maybe less than 100 candidate craters. It's hard to find craters on Titan because it's still, for small craters, it's hard to see through the atmosphere with high enough resolution. But other moons have thousands of craters. So that indicates that the surface is pretty young, which means it's been refreshed through some kind of geological processes. There's also the fact that Titan has this dense atmosphere, which means that some smaller craters might get burnt up just like they do on the Earth, or smaller meteorites. Another interesting fun thing about Titan, the equator is mostly covered in, just like the Earth again, in sand, in dunes, except for the sand isn't made from silicate rock. It's, again, we think it's made either from broken up dirty water ice or from this organic material that seems to be prevalent all throughout the atmosphere. The dunes, if they're forming like this, that means that there is wind processes that's blowing this sand around. And by looking at the dunes and what they look like, we can actually learn a little bit of something about the winds on the surface of Titan. So here, all these dark regions are dunes. These brighter regions that they're kind of moving around are just some kind of different material that must be a little bit stronger because it's not getting broken up by the same erosional process. So it's blowing around those regions. Okay, so we go back to the methane cycle. I didn't mention one of the things that is interesting about Titan. Okay, so we know that in Titan's atmosphere, the methane gets dissociated or broken up by absorbing sunlight. Okay, so energetic sunlight comes in, it hits a methane molecule, it breaks the carbon from the hydrogens, and molecular hydrogen is a really light gas. So in a body like Titan and even Earth that doesn't have a lot of gravity, it just escapes, okay? The only planets that can really hold on to hydrogen are the gas giants. That's what makes them giant. So that means there's a big sink for methane in the atmosphere of Titan. And we think, in fact, the amount of methane in Titan's atmosphere could only have a lifetime of something like 10 to 100 million years, which isn't very long for a planetary scientist or geologically. Okay, and if there was no methane in Titan's atmosphere, Titan would be really boring. Methane is a greenhouse gas. It actually causes the atmosphere to be warmer. So if we took out the methane, the nitrogen, which makes up most of the atmosphere, would get so cold it would freeze out or condense on the surface. So we wouldn't have this interesting atmosphere. And of course, without the methane, we wouldn't have all this interesting methane cycle going on, all the liquids and the precipitation and the clouds. So methane is important, but it seems to be a temporary feature of Titan's atmosphere. And the truth is we don't really know the answer to why it's there, or maybe it's only been there for 10 million years. We don't really know. But if we look at this picture, scientists think there might be some outgassing of methane from in the interior of Titan. So maybe there's a reservoir of methane under the surface of Titan that gets outgassed through volcanic processes, which also, again, kind of happens on Earth. And what this is called is cryovolcanism. It's volcanism that's not that different than the Earth's, other than it's happening at much colder temperatures. So Cassini looked and looked and looked for good evidence of cryovolcanism, and frankly, it didn't find a smoking gun. This particular Sotra facula, I'm not sure if I'm saying that right, is the best candidate for cryovolcanism on Titan. This is a fancy image made from radar data. This is what it looks like in the radar data. And it kind of just looks like a cryovolcano. You got a peak, a pit, which is like a caldera. And then these regions look like they could be flows. And the flow is mostly going to be water ice acting like magma on Titan, but it's also going to release gases with it, including methane. All right, so going back to Titan's atmosphere, I talked about how methane is broken up in the very upper regions of the atmosphere by absorbing sunlight. It also can be broken up by energetic particles coming in from space. This is the fundamental thing that drives the chemistry that causes Titan's atmosphere to have that orange color. Okay, that orange stuff is basically like the smog. So if it's smoky outside, or maybe if you go to a big city on a really bad pollution day and the atmosphere starts looking opaque, it's because there's a lot of organic material in it. Well, at Titan, it makes this organic material naturally. And what drives it is breaking apart, again, the methane and the nitrogen. Chemistry happens. It starts making massive particles very high up in the atmosphere. Those particles combine to create what we call aerosols, bigger things. And as it gets heavier, it all just slowly rains through the atmosphere and starts to cover the surface. So the dunes, for example, the source of that material, it could less be like sand. It could be more like snow coming from the atmosphere. We don't really know. But we do know that if this process has been going on for a long time, Titan's atmosphere has made a lot of this organic material naturally, okay, this orange organic material. And that takes us to another reason why Titan is so interesting to planetary scientists and scientists in general. This orange stuff is organic material, okay? It's got big carbon chains in it. And if you know anything about biology, biological molecules are similar. They're big chains of carbon, okay? So these could be prebiotic materials. And in fact, there's a famous experiment called the Miller-Urey experiment that tried to replicate what it thought the atmosphere of the Earth was like before life put oxygen into the Earth. Okay, so oxygen, all the oxygen in the Earth's atmosphere today is basically from life. So before there was life on the Earth, the composition of the Earth's atmosphere was quite different. So this was maybe not actually accurate. This was what it was thought to be at the time. But if you sparked this atmosphere, what you saw was you dissociated these molecules and you formed orange stuff, very similar to what's formed in Titan's atmosphere, which they call tholins. Okay, if you mix these tholins with water, you can form pretty easily amino acids. And amino acids are the building blocks for protein, and proteins are incredibly important for life. So scientists think by studying this chemical processes on Titan, it's like a big chemical laboratory where we can maybe understand how some of the organic material that we think we need for life could have formed naturally, abiotically, without life on the early Earth, which may have helped the origin of life happen. Okay, so we don't really know how any of that happened, but that's an interesting reason to study this big orange atmosphere. So Titan is relevant to understanding the early Earth, and we think it's relevant to understanding life. So one of the theories for how life started, which was popularized by Darwin, that's who this is in this image right here, is this idea that we have pools, right? Organic pools of water. We know water is essential for life, so maybe you got some warm water, and this idea maybe with Titan and Earth, early Earth, is maybe you've got a lot of this organic material raining down from the atmosphere into these warm, friendly pools of water, which we could call a primordial soup, and life somehow originated out of that. Okay, hasn't been proven, just an idea, but that's one of the reasons why scientists study or want to study the atmosphere of Titan. So going back, now I'm going to talk a little bit about what I do. Okay, so I said at the beginning that I don't do a lot of stuff that involves pretty images. I like when I talk to the public to show those because I think they're really fun to look at, and one of the things that makes Titan interesting. But what I do is study data from the particles and fields instruments. So these are the instruments that are measuring stuff in situ, in place, plasma densities or gas densities, magnetic and electric field magnitudes, things like that. But it's still relevant to some of these other bigger questions that I just talked about related to Titan. So one of the big surprises from the Cassini's mission was that these organic molecules, heavy stuff, massive things, form really high up in the atmosphere. So this, I don't know if you guys can see this, this is about 1,200 kilometers. The analogous region on Earth would be just below where the space shuttle flies. So many miles up, tens of miles up in our atmosphere. And it was such a surprise that you'd find these heavy molecules that high up that in fact, we quickly saturated the mass range of the instruments that were designed to measure the density and the composition of Titan's atmosphere. It went up to 100 AMU, or basically 100 times the mass of a proton. We think that there are ions at that altitude that are as massive as 8,000 AMU. Okay, and one of the fun things you can do with spacecraft is use some of the instruments for things they're not supposed to be used for. So this is data, this is mass versus density or counts from an instrument, the ion neutral mass spectrometer, that is designed to measure the density of ions at different masses in Titan's atmosphere. This data here is from the electron spectrometer, which is designed to measure the density of electrons. Nothing to do with ions. And I'm not going to go through this in too much detail, but these spikes that you see in this color graphic were a surprise. And they didn't make any sense for a while. And then they finally figured out these spikes were actually negative ions, which got into this instrument that's designed to shield positive ions, but not negative ions because it's designed to measure electrons. Heavy negative ions were getting in and hitting the detectors and causing these spikes. And by using the actual velocity of the spacecraft, you could figure out the mass of the particles based on the energy that they were observed at. Anyway, so we were able to figure out how massive the particles were using a totally different instrument. So this was all happening, like I said, in the upper atmosphere. This is the region that Cassini is actually flying through in the thermosphere. at Titan, that's about 600 miles up from the surface. So Titan has this really extended atmosphere. And we're already seeing these really interesting organic materials forming. And again, that's analogous to the thermosphere on the Earth. So that would be where, say, below where the spacecraft or where the shuttle flies or flew, but similar to where we get aurora and polar light. So really high up. So this is kind of what I study. So going back to this graphic, I'm studying this part of it, how the energetic particles come in and kind of help initiate this chemistry. And it's analogous to studying the aurora on the Earth. So the aurora that we see at the polar regions of the Earth, that has to do with charged particles coming in from space into the Earth's atmosphere and exciting the neutral atoms. The same kind of thing is happening at Titan, and that's part of what is helping drive the chemistry that makes these big, interesting organic molecules at Titan. And so again, I'm studying this part of the interaction. I do it with big computer models, and I'm not going to get into the details too much, but basically what I'm showing here is the results of those models. And what I'm trying to study is the flux of how many of these particles, these energetic particles, are coming in to the atmosphere. Where are they coming into the atmosphere? And once they get into the atmosphere, what do they do? Okay, so that's my piece of this big puzzle. It's way, way, way high up, way further up than the surface with all those pretty pictures. But that's my contribution. People often ask me the coolest thing that's related to my science, at least, that I think Cassini discovered. And one of the most interesting things that Cassini found was also a surprise. And that's when it flew by this very white moon in the solar system known as Enceladus. It's a small moon, much closer to Saturn. And Enceladus, when Cassini flew by Enceladus, it actually discovered that Enceladus had these plumes of gas coming out of its southern hemisphere. And the regions they were coming out of are these regions here, which they called tiger stripes. And the plumes of gas were oxygen containing molecules, so a lot of water essentially. And the water gets dissociated and also ionized when it interacts with the sunlight. And when it gets ionized, it actually gets transported out to Titan. And so one of the energetic particles that comes into Titan's atmosphere is this oxygen that was originally in the interior of Enceladus. So I think that interplanetary transfer is really cool and interesting. So my goal for this talk, again, is try to convince you it's the most interesting body in the solar system. One of the reasons to do that is so that you look forward to future missions to Titan. So I just want to end with some information about what's happening next and maybe some concepts that people talk about. It's really easy to fly on Titan. Titan has a very dense atmosphere, so it's 4 times the density at the surface. And it's got really low gravity. The gravity is about the acceleration of gravity is about 7 times lower on the surface of Titan than it is on the Earth, okay? So when people give public talks, they often say humans can fly by flapping their wings on the Earth. That is true. You would need some kind of wings. You can't just do it with your arms. But if you gave yourself some sort of wings or a glider or something, you can generate enough power with your muscles to actually fly on Titan. The atmosphere is so dense and the gravity is so low. So a lot of the future concepts take advantage of that. Titan would be great for balloons, okay, which I'm totally into. I love high altitude balloons. So I love the idea of having a balloon taking data at Titan. Airships or blimps has been proposed. This is a mission that I'm actually helping to develop, and that's sending probes into some of the lakes, okay? But a mission that actually has been selected by NASA that's coming is related to those things, and that's the Dragonfly mission. And the Dragonfly mission, this is a graphic here showing what it looks like. It's what's called a multi-rotor vehicle or a rotorcraft, which is basically a drone, okay? It's a drone with more rotors. Again, it's gonna, especially with drones today, kids have them, everybody has them. They're not that hard to fly. It's not hard to fly a drone on Titan either. This mission, the drone is gonna be like a fancy rover. So we send rovers to Mars and they drive really slowly and carefully, blah, blah, blah. They take forever to get everywhere. This guy can just land, take some data, go and then hop, or maybe a survey the area, decide where it wants to go next, come back and then hop again, boop, land pretty far away from where it started, and sample maybe a dozen regions on Titan, just kind of flying around. So that's what it's designed to do. When it lands, it's going to measure the composition of the surface, try to figure out what the material is. It's going to land in those dune regions, so it's going to probably stick around the equator. When it's flying around, it's going to measure properties of the atmosphere. And it's basically going to address a lot of the questions that we were left with after looking at the surface so well with Cassini. So I thought I would play one more quick movie here. This is just, again, when you have a future mission, you got to make some fancy movies to get people excited about it. This is showing you guys what Dragonfly will look like. And again, we have to wait a little while before Dragonfly gets there, so it's going to be a long time coming. The rotocraft will actually be autonomous, so it's going to be sensing its own environment and deciding how to fly. There's a big communication leg between the Earth and Titan, so it's got to fly on its own. It's going to be powered by a thermonuclear generator, just like Curiosity is. Anyways, I think that's pretty cool. That's one of the coolest missions that I've seen. All right, I think that's my last slide. Yeah, so I'm going to end it there. A little bit long, apologize for that. And this, by the way, is the last picture that Cassini took of Titan. It's a mix of visible and near infrared, which allows you to see some of these features of hazes. And I'll open it up for questions.
Great, thanks. That was awesome. Every time I see a video of Dragonfly, I think that is the craziest mission.
I know. I should say I am not associated at all with the Dragonfly mission, and that's because my science is so much higher than what Dragonfly will do. But yeah, it looks crazy, but then you remember that 4-year-olds have no problem flying drones on the Earth, and it's actually easier to fly on Titan. The biggest problem is power, I think, and communication. I was surprised that you can actually get data from the surface of Titan to the Earth without a transmitter, but apparently they can do it.
Yeah, well, that's great. We have a question from YouTube. Julie asks, are the methane seas located at the poles of Titan?
Yes, they are. They are located at the poles. As far as we know, there are no lakes or seas at the equator of Titan. And yeah, it just seems kind of like the Earth, the equator is just dry, and that probably has something to do with the atmospheric convection. But it also could have things to do with the surface and how moist the surface is and stuff like that. And how long, if something were to rain on the surface, how long that liquid would actually stay there before either seeping in or evaporating.
Yeah, do you want to say something a little bit about the climate or the meteorology that's driving the liquid to the poles of Titan?
Not
to put you on the spot.
Yeah, I mean, I can't say too much about it. That's not really my specialty, but I mean, it just has to do with what's called Hadley cells on the Earth. Or, well, you can think about it a couple ways. So what actually causes those clouds to form that cause precipitation would be Hadley cells. But then there's larger cells of seasonal transport of material. So for Mars, for example, like carbon dioxide at Mars, it sublimates. So it kind of goes straight from solid to gas form. And you see this transport of the carbon dioxide of Mars seasonally between the poles. And so it's likely that something similar is happening on Titan. And again, it has to do with changes in the season and what's exposed to the sun and getting heat, and what's cold, causing changes in big circulation patterns of the atmosphere. But at Titan, you can actually, instead of having it go straight to a solid, you can get it in a liquid form. That's kind of my understanding of it. But again, I'm not an expert in that, but that's how I understand it.
Any questions from our local folks? Do you guys in the local Zoom? I mean, I can ask questions forever, so I want to make sure that other people have a chance to ask questions. Can you see the chat window there?
I can't.
That's fine. I can read it for you. It's no problem. How strong are the winds on Titan?
They're not very strong near the surface. That I know it's something like 2 meters per second, 2 to 10 meters per second. So there are some winds, but they're not super strong near the surface. Up in the higher altitudes, just like on the Earth, you probably get some higher winds, like the jet stream, but not super strong, but strong enough to transport that material around to form the dunes. But Titan also has a lot lower gravity, so that's not as hard. Super interesting. It's a different planet with like same things going on, but different parameters.
Yeah, the winds at the surface of Titan are really weak, like probably not a meter a second. That's and
no, I actually wrote that down. You don't think that? Let's see. I thought I wrote that down. I did think about that when I was talking about the dunes. I was like, someone's going to ask me about the winds.
Yeah, and so I think the dunes in some cases can be driven by seasonal winds that are much stronger than usual. So when that Hadley cell circulation kind of flips.
No, not yet. Probably not a couple meters a second. Maybe a couple meters per hour. Probably getting the units wrong. So sorry. But they're not very strong, I would say, at the surface. It's not a problem for Dragonfly flying around, essentially. And they wouldn't be very strong, again, because the solar heating at Titan is a lot less than it is at Earth. And that's essentially what's driving the winds at the Earth.
Another question, is Titan's orbit on the same plane as Saturn's rings? And do you know how far away it is from the ring's edge?
It is on the same plane as Saturn's rings. It is probably, what would it be? I don't know if I can give you a distance in like miles or something, but Titan orbits at about 20 Saturn radii away from the center of Saturn. So probably depending on where you want to put the edge of the rings, I don't know, something like maybe like 17 Saturn radii. So Titan is compared to, there's a bunch of inner moons that are quite close to the rings. Titan is pretty far away from Saturn compared to those.
Yeah, that's fascinating. Do you want to say something about the mystery of the lifetime of methane in the atmosphere? You may have mentioned this. I don't know if
I talked a little bit about that. So we think the methane has, depending on the model, and again, we don't fully understand the loss rates of the gases in the atmosphere. That's one of the things that I kind of study a little bit. That's still an open question after Cassini. But we think that the amount of methane in Titan's atmosphere now would only survive for something between 10 million and 100 million years, which sounds like a long time, but it really isn't a lot in terms of planetary timescales. So that either tells us that the methane in Titan's atmosphere is some temporary feature that maybe hasn't been there for the whole lifetime of the moon Titan, or it tells us that maybe there's something replenishing the methane in the atmosphere, something from the subsurface or something like that, which is also a possibility. That's why I talked about cryovolcanoes. That's kind of the main thing that people think could replenish the methane in the atmosphere, but we didn't find super good evidence. I mean, we didn't find necessarily, it was just, they're hard to find. So it doesn't mean that they're not there, the fact that we didn't find them. And we did find like that one good candidate that I showed you, but we didn't find a smoking gun for it.
A question in the chat window here is Dragonfly going to collect any physical samples like rocks or any materials on the surface of Titan?
Yeah, actually I did I'm gonna cheat a little bit. I didn't put this video in. I think this is the video I want.
Saturn's largest.
Maybe mute it. Yeah, okay. I might turn the volume down just so you can kind of see what it does. It's gonna drill holes and then it's actually gonna suck the material up through these tubes. It's really cool. And then the tubes are gonna put the material in these little sample bays, which are gonna put it in mass spectrometers essentially. So, and gas chromatographs, which basically just heat the samples up and see what kind of gas comes off of it. So it doesn't have an arm to pick stuff up like Curiosity does and scoop and move it around, but it's going to suck it up. And they chose this because I think it's a little bit safer mechanically. It's less likely to fail than an arm would, but that's how it's going to sample the surface. And it's going to have a couple of those in case one of them breaks. And I don't know what all these things are. I guess these are all the different, I don't know, maybe you can't reuse those. So they just have a bunch of these little, I don't know, sample containers that it goes into. So that's the plan. Pretty cool.
That is crazy.
Yeah.
Yeah, here's another question. Can you say anything about the significance of a lack of an internal magnetic field? What is that telling us about like the interior of Titan?
It's not necessarily surprising. So if we look throughout the solar system, the only bodies that have an internally generating magnetic field are bodies that we think still have some liquid material in the interior. So in the Earth, there's a liquid iron outer core inside the Earth that actually convects and generates the Earth's magnetic field. Mars, which is smaller than the Earth, doesn't have a magnetic field. So it's more like Titan. And we think that's because Mars is smaller and it actually probably has cooled more rapidly than the Earth or sooner than the Earth. And so if it did have a liquid core, that core has cooled off and is now solid, and that shut down the magnetic field. So for these moons, because they're small, we're not actually surprised that most of them don't have magnetic fields. The only one that does is Ganymede, which is the largest moon. That does have its own internal magnetic field, and that is kind of an anomaly. So it's not surprising that it doesn't have a magnetic field. Maybe what's more surprising is one of the results of Mars not having a magnetic field is that we think that the solar wind is actually stripping the atmosphere of Mars away. And there's a spacecraft that has been studying Mars for quite some time now called MAVEN that's actually trying to figure out how rapidly that's occurring. And that's part of why or how we think Mars has lost water from its surface. It went into the atmosphere and then it got stripped away. If Mars had a magnetic field like the Earth does, that atmosphere might be protected and it could still be dense and there could still be liquid water on the surface of Mars. So the fact that Titan doesn't have a magnetic field is also kind of interesting because it does have a dense atmosphere, even though it doesn't have this protection of a magnetic field. So it could have gone either way. I mean, we could have measured a magnetic field, and because Ganymede has one, scientists could have been like, oh, okay, so it's got, a magnetic field. But basically it says the center of Titan is probably a solid. There's nothing that can convect and generate a magnetic field.
Yeah, really fascinating. Another question. Someone asks, why doesn't Ganymede have a thick atmosphere like Titan?
That's a good question. That I can't tell you. I don't know. It could have something to do with the fact that Ganymede is closer to the sun than Titan. That's probably the main reason. So they're both very cold, but Titan is colder than Ganymede. And colder gases have less thermal energy. So they're basically moving around not as fast. And because of that, they're easier to hold on to. So even though Titan doesn't have a lot of gravity, it helps that its atmosphere is really cold. That helps it hold on to it and keep it gravitationally bound. If you were to move Titan in to where Ganymede is around the sun, the atmosphere would heat up. And I suspect Titan would quickly lose its atmosphere because of the motion of the gas.
Yeah, really interesting. Okay, any other questions? All right. Well, thanks so much for attending, everyone. I'm going to get you to stop sharing your screen.
I can do that?
Yeah, that'd be great. Yeah, that was really excellent. Thanks so much. Really fascinating. Honestly, I've got people in the chat window saying that Titan is the most fascinating. They're convinced now that Titan is the most fascinating body in the solar system.
Good. I've done my job.
Right.
Vote for Titan.
Yeah, I totally agree. Yeah, so thanks for joining us, everyone. As I said, the next one of these will take place on October 2nd, 7:30. We'll have Dr. Laura Mayorga from Space Telescope Science Institute. So that should be a really great talk. And Darci, let me get you to stick around right after this.
Okay.
Have a good night, everyone. Great weekend, and we'll talk to you later.